So while the next speaker is setting up, let me introduce him to you. So the next talk is by Sharos Khan from Strathclyde University, and he'll be talking about shape signature subspace, so how to reduce the dimensional space in shape optimization.
Thank you, everyone. First of all, I will try my best not to go towards a lot of mathematical details. It would be nice to show you this one because of the time constraint. I will try to skip it on. So this is a joint work between the University of Strathclyde and Institute of Marine Engineering and Redcution University. So I guess everybody here has once used optimization or shape optimization. Whenever we talk about shape optimization, we heard a lot of these terms. And we somehow try to deal and try to overcome these difficulties or these problems within our shape optimization pipeline. I don't think I have to give you a background a lot what the typical shape optimization pipeline is, but let's say we start with a design under consideration, we parameterize the design, and we build our design space. With this design space, we integrate a shape modification function which just give us shape variations which then optimizer gonna explore with the help of the solver. And this process will continue until we reach a satisfactory design or let's say an optimal design. But in this case, you can tell me, like, come on, you're only doing the parameter or shape optimization with only 3 design variables. We definitely cannot have the best design possible. Why not enriching your parameterization? Okay, of course. We will have much better design variations or diverse design variations, but we will come across a problem of high dimensionality. With this dimensionality, we all know this notorious curse. That's a curse that occurs in the shape optimization pipelines. Because if we have high dimensional problems, that means we need to exhaustively explore our high dimensional space, which I represented as a hypercube. And with this one, we need to perform larger, let's say, design evaluation with this expensive computational solver. So this increases our computational cost, and that cost is mainly associated with the 3 components of the shape optimization pipeline. One goes towards the performance evaluation, other somehow towards the shape modification process, and then the optimizer itself, like what kind of optimizers we're using. It's okay. So in literature, there exist a lot of techniques. So I will mainly focus here on the dimensionality reduction. So what happened in this case, we try to extract some geometric information about the shape and then construct our subspace. So the analogy here is that because when we have a shape variation, not all the geometric variation is so important. So we can exclude the lower variations of the geometry, only have the higher variations. So that means if that will result in higher, let's say, design improvements. So we will only use that and then construct a relatively lower dimensional design space and do our shape optimization pipeline. To extract those geometric features, we have well-known problems, let's say PCA, which goes by many names, KLD, proper orthogonal decomposition, and then we have some nonlinear extension of these approaches. And recently, due to machine learning, we are also, engineers especially, moving towards AutoEncoders to extract such kind of features from their data sets, from their geometric representations, and adversarial networks. So they all work quite well. But there is one problem that I at least faced by using any of those techniques, that the parameterization that we get afterwards, it doesn't generate any smooth geometries. It's mainly because the shape that we're trying to work on is complex, and there is like a lot of intrinsic complexities under the shape. So we can't have a geometry which have a compact representation. We will have many infeasible designs. We will have many invalid designs, and because I told you that the analogy here is that we exclude those small features from the representation, say because they will not perform much improvement in the design. That necessarily not always true, so there is no information related to physics. So which in optimization results in that we always most of the design that we tend to explore, that also Martin talked about, that they are invalid or infeasible to generate. But of course, our solver can avoid it, but that means we will have to evaluate and pay the cost. So this mainly happens because of I would say two main reasons, because the geometric representation that we are giving to those techniques that I mentioned in my previous slide is just merely a discretization. There's not a highly representation of the geometry that we're giving in. And there's no information about the physics. Okay, there's approaches called reduced order modeling where we do the reduction, do the same stuff for the physics, but not in the geometry. But that means that's something completely different. So my idea was, okay, because as I said, there is no information about the physics, and the geometric representation that we're using, it's just a discretization. So why not I add physics for learning my features, and with these features I get my subspace, and then because this subspace has quite a lower dimensionality than my original space, and then I perform shape optimization and hope that the convergence would be much faster. But if I want to directly include the physics, that means I'm making my shape more supervised in its way. But that means still at the offline setting, I will have to evaluate a lot of designs, construct a data set, and then perform this one. So yeah, this still the problem of computational complexity will still exist. So my objective here is that why not I extract some high-level representation from this geometry, okay? And this representation have also some knowledge about the physics, but it's not exactly the physics, and it's computationally expensive to evaluate. And I put both the geometry and the physics in an envelope, and then I construct these functionals, and these functionals, as I said, have all three quantities. The qualities. And then instead of directly including the physics, I use those functionals with the physics, with the features that I'm getting from the geometry, and construct the subspace, which is more or less, let's say, compact, diverse, and physics integrated or physics informed. So when we have these features, we call these features as geometrically and functionally active latent variables. Geometrically, because I said we're using a high representation of the geometry, and these functionals that we're using, they have also some knowledge about the physics, so they are also physics informed. That's why we call them functional. So at the end, the resulting subspace we have its physics informed, and high representation capacity means it will generate mostly feasible designs, and the design will be diverse, so we can have a better optimal design at the end. So we call this over a shape-supervised approach, because it's directly not supervised, because we're not directly using the physics. We're extracting some information from the geometry and integrating it, and that's why we're calling it shape-supervised. Okay. So consider we have a design which is parameterized with a certain number of parameters, and this parameterization giving us a certain design space with upper and lower bounds, and depending what type of parameterization optimization we're using. And then we have a shape modification function given a set of parameters. We have this t, and then we give it this parameter with the parent or the initial design, and then we get a new modification of the designs based on these parameters. So in terms of, when I say dimensionality reduction, I want to have a lower order representation of this function. So which, instead of taking this t, which is composed of, let's say, few 50 or 60 parameters, it takes only certain, let's say, 5 to 6 parameters, but captures all the representation that exists in the original space. Okay. So the idea here is that we have this function, which is a continuous shape modification functions, and we add another functions. So this function, it's widely known, it's called moment vector. Okay. I will talk in the next presentation, in the next slide, what's the vector about. We take this and we construct a new shape modification vector function, which we call shape signature vector. So these moments and the shape modification vector act as a descriptor. It's like uniquely represents a design or a geometry in the design space. And along these two vectors, they are, let's say, in the joint Hilbert space, and then they have this generalized inner product. And within this space, we're going to learn a lower dimensional representation of our geometric modification. Okay. So the geometric moments, why do we choose geometric moments? What geometric moments are? Geometric moments are basically the intrinsic properties of the geometry. And these moments are integral properties. They have been widely used in differential geometry. And these provide a medium for many types of physics analysis. Those analyses are depending. the underlying formulation on these integrals. In mathematics, they're represented as a Riemann integral, and they're evaluated we evaluate them in the divergence theorem. We convert the volume integral into the surface integral, and then we evaluate this integral. The one common example of these integrals are the first order geometric moment is the volume. The zeroth order geometric moment is the volume, and widely use it. So with moments of a certain order, make this shape modification vector, for example, if the moment is of order 2, we have 6 components of this in this function, this vector, and then we use it. Okay. So basically, as we start from a zeroth to the larger moment vector, we are capturing more and more representation of the geometry. This is just to give an illustration that as we go further, we're going to have more cost for evaluating these integrals, but we will capture more representation. So they have been used in many different applications, ranging from computer design, in computer vision, and many other physical analysis. Okay. So as I said, once we have this safe signature vector, okay, so our aim here is to extract this lower dimensional representation of our original shape modification vector, which is depending on a large number of parameters. So typically, instead of now performing shape modification directly with this high dimensional representation of shape modification functions, we construct a lower dimensional representation, which is based on some lower number of parameters, which is parameter vector, which is v. So with this lower dimensional, let's say, representation, we will have a lower dimensional design space. Okay, so how we do that, we basically apply KLE, the Karhunen-Loève expansion of this one. And the problem for KLE is that we want to construct the optimum orthogonal basis for our shape signature vector, SSV. And for this, we want to solve this optimization, whose solution will be, the eigenvalue solution would be the orthogonal basis for our new representation. Okay, so once I said that in the previous design spaces, we had 3 typical problems that our design space wasn't, the subspace wasn't compact, it wasn't diverse, or it wasn't physics informed. So once we have, let's say, constructed a new subspace, which we claim to overcome all these limitations, so how we measure this? So for representation to richness, we use this horse of distance. Horse of distance, it measures the distance between the 2 designs without like what's the point-to-point correspondence. We sample a lot of design over design space. We measure from the initial design or the parent design the horse of distance, and we average it. If a design space, let's say A, gives us a higher average distance, that means more richer than the subspace B. So we have the compactness, so we measure that how many invalid designs a subspace is giving us. And in terms of physics informed, if we perform the shape optimization in the new space, is it giving us a faster convergence? That means, is it physics informed? It does have some knowledge of physics or not. So we have these 3 test cases. We have these 4 test cases. And then we have many experiments, and we have performed many experiments for different order of moments. But in this presentation, I will just show the results only for the 3rd order. And the criteria for us, how much geometric variance we want to capture in our subspace, is 95%. So we are allowing 5% of error while having this conversion from higher to lower dimensional design space. Okay, so this is something really interesting results. So in original, let's say in case of airfoil, we had original 11 design parameters, so that our design space was 11 dimensional. So we typically with PCA, we could achieve 6. But with oversetting, this SSDR, the shape-supervised dimension reduction, we could achieve 4 parameters with 63% of reduction in the set of parameters. And similarly, the same trend with all the other, let's say, test cases. The interesting thing is here is that the wing model we constructed with 3 different airfoils, which was parametrized with 11 parameters. So in total 33, but at the end, interestingly, we had 11 dimensional design parameters. That means we can say that only 1 aerofoil was enough to have the design variation in this 3D wing case. So okay, so to see how much invalid designs were coming out. In the original setting, the PC setting, you can see here, there's a large number of 50% designs were invalid, 20% of the design was invalid. Compared to overcase, it's much less, only 10%. So we can say that the over technique is able to produce a more compact representation of the geometry, able to extract the more compact representation of the geometry, so resulting in much lower number of invalid designs. So the invalid designs are the ones which have self-intersecting surfaces or the curves. Curves in 2D case and surfaces in 3D case. But in terms of, let's say, design diversity, they are the same. That's something really good, because we were expecting that if we exclude all the invalid designs, so in our case, we will have less diversity within our design space. So for optimization, we solve an optimization problem, a very complicated optimization problem, which is to minimize this wave resistance coefficient, which is with a set of different constraints. So wave resistance coefficient, it's a criteria, or it's a physics performance when a body or a ship moves through the water, and how much it's same related to the drag, how much it has a resistance to it. It's computationally expansive, it's sensitive to the local features, and it's crucial to minimize it at the preliminary design stage. So in terms of optimization result or convergence, you can see that with the design space, subspace constructed in the OR method have a huge, faster convergence compared to the one that's constructed with the typical methods of the PCA. And the optimization shape in the over case was also doesn't look wiggly or doesn't look invalid. And these lines just represent, like, we put section, and then we compare that is the gray line is the parent design or the initial design, and then this blue one is optimized. So in conclusion, that we were able to with the inclusion of the moments, we were able to simultaneously solve all the three problems. We are able to construct a compact, diverse, and physics-informed design space. But the drawback is not all, because at the beginning of my presentation, because most of the physics criteria are depending on these geometric integrals, but not all of them. So we can't say that for every problem, the subspace you will construct with our technique will be physics informed. The other work is we want to explore this for not only case of a linear representation, we will also go to a non-linear representation, let's say in case of AutoEncoders and GANs, where we include also these integral properties during the training and see what kind of results we're getting. So that's it from me, and to acknowledge some of the findings, and the code is freely available, and if you have any questions, I would